Hello everyone, my name is Luca Tedesco and I'm an independent vulnerability researcher from Venice, Italy. And I've been focusing on Apple's products and I'm very attracted by jailbreaking techniques. And I'm the author of several XNU kernel CVEs and exploits, which I've been open sourcing on GitHub and Twitter. And the XNU kernel is a quite big target for jailbreakers, but in Yosemite, Apple has started enforcing kernel extension signatures. But in El Capitan, they also introduced system integrity protection, which is a system-wide kernel-enforced sandbox profile that prevents access to system resources. And there are several ways to bypass this, but attacking the kernel is a viable way to disable it and bypass also the sandbox. So I'll be starting with a very brief introduction on the kernel heap. And in particular, I will be talking about Zalok, which is the zone allocator. Most other allocators rely on Zalok. There are three functions which you can call: Zinit, which can create a zone, and Zalok, which allocates an allocation of a zone, and the free, which frees an allocation back into the free list. And each zone has a last in first out linked list containing free chunks, and allocations in a zone are same sized. When you allocate from a zone without any free chunks available, a new page is mapped in, and the page is split in chunks, and each chunk is added to the free list. This allocator has been discussed very much by Stefan Esser. So if you want to detail more about it, you can just read his papers. But for exploitation, what we care about is that there is 9-line metadata for allocated chunks, and there is free list metadata on free chunks. But the free list metadata has been hardened since iOS 6. These days, application metadata is the most common target. And I say the only one because, after all, you can do pretty much everything by corrupting application metadata. Different zones use different areas of memory, so you can't do a heap buffer overflow in a zone and corrupt another zone. But this does not apply to large allocations. So if you have an allocation which is larger than the page size, you can pretty easily get an adjacent allocation from another zone. And then there is Calloc, which is a more malloc-like interface to Zalok, which registers several zones with the various sizes. The only difference between Calloc and malloc is that when you use free to free a block, you also have to pass in the size because, as I said, there is no inline metadata in allocated chunks, and so free has to pick the right zone to free the allocation back on. This is the output of the print calloc, which shows you all the zones registered by calloc. This does not work in El Capitan for some reason, but just running the print grep calloc should work. So I don't know why, but it is. For application metadata, there are several targets. The most common one is VM map copy, which has been introduced by Terje Mand and Mark Dowd in their iOS 6 security presentation back like 3 years ago. And it's just a structure that is used to represent a copy of some data. And if this data is smaller than a page, the kernel heap is used. Many jailbreaks have targeted this structure in the past for various reasons. The biggest reason why this structure is very good is because you can control the size which is passed to calloc when you create it from userland. And so you can just put it in any zone, and you can do pretty much anything with it without being affected by sandboxing, but just using mock messages by using out-of-line data. So this is the structure in before El Capitan. And as you can see, there is a size, there is a pointer to the data, and there is also the calloc size, which is used to free this structure. So if you want, say you have a heap buffer overflow, you can just corrupt the size or corrupt the data pointer to do arbitrary info leaks. So here's the anatomy of a pre-Capitain kernel exploit, Capitain, which I've been working on, and I've released in August this year. It used to be 0-day at the time, and the core issue was type confusion in handling MAC ports in an IOKit function. I'll explain more about this later, but first I have to explain page 0. Page 0 is essentially the first page in another space on a Mac process. And essentially it's used to trap all null pointer dereferences. Linux does this as well. I'm not sure about Windows, but probably Windows as well. And Apple enforces this in kernel, but not for 32-bit binaries. So if you have a 32-bit binary, you can just skip the page 0, and you can allocate whatever you want at null. This is important because, as you will see, IO service open extended accepts various arguments, and these are converted from userland to kernel land by essentially MIG, which is an automated interface generator between a Mac client and a Mac server. When you pass arguments to a function that travels MIG, essentially MIG itself serializes and unserializes all the arguments you pass in. But in this particular function, you can't see much, but there is no check on the task you pass in. And so if you pass in a task which is not actually a task, it will pass it down as null to the user client. User clients are essentially a driver object which can be used in userland. Code runs in kernel land, but you can call every function you want from userland. And when you create one, you essentially pass in the task, and a particular user client, which is the disk image one, uses this task structure to read a pointer, and it will do an OR on the pointer, which, if you do the type confusion, is read from page 0. And so we can essentially corrupt memory in kernel as we wish to anything we want. So first of all, we need to locate something. And for this, I used a HIMP infoleak to locate an object in a calloc. But we need to locate a VM map copy to be able to do arbitrary infoleaks. And then we have to corrupt the VM map copy. From there, we can derive the KSLR slide. And from there, we can just run ROP in kernel. So this is the kernel heap. But it's fragmented, so I allocate 2 objects, leak the pointers. They are not adjacent, so I free the first one, and then allocate a VM map copy in, and allocate a new object. From this new object, we leak the pointer, and we see it's not adjacent, so we free the first object and allocate a VM map copy in as placeholder. So we allocate another object and leak again. These 2 objects are adjacent, so we can just free the first one, allocate a VM map copy in, and then we have this memory layout. And we know the pointers to both these structures. So we use our memory corruption primitive to do this, essentially. And once we do this, we can read past heap boundaries and have read access to the vtable pointer of C++ object, which points to the kernel data. And kernel data is led by the KSLR slide. And by just doing a subtraction, you can find the ASLR random value. And this is the result. Local privilege escalation. It can also be implemented in a sandbox escaping way. But yeah, this was before El Capitan. However, in El Capitan, the structure has been changed a lot. Essentially, what they did was to remove the size to free and remove the key data pointer. So now we just have a structure which contains type, an offset, and size. And we can't do much with this because if you change the size past heap allocation boundaries, you will cause a wrong free in the wrong zone, and it will corrupt the adjacent allocation. And the pointer to the data has been removed. This prevents us from reading a pointer to the adjacent VMAP copy by putting two VMAP copy one after the other. And you can't write into this pointer to leak arbitrary kernel memory. For this, you need new techniques. But for adjacent data, we can just corrupt and then rewrite the leaked data so it doesn't actually look corrupted, but the internal heap state is corrupted, so you have to clean up later. And it's also not very reliable because it involves a reallocation, and if you get scheduled out, another task might create another location which falls into the place where you freed the wrong zone, and that will crash the kernel very likely. But we can do this. And since you can't read the data pointer of another structure like this, you have to find another structure to do a heap info leak. And the free list is an easy target. So you can just allocate two adjacent VMAP copy structures, free the second, and corrupt the first to increase size past heap allocation boundaries. By reading the first VMAP copy out, you corrupt the memory, but you also leak the free chunk. And by leaking the free chunk, you can allocate a new VMAP copy with the free chunk in, and the kernel won't crash if you do this, but you will be able to know a pointer to the next free allocation. So if you create two new VMAP copy structures, you will know the pointer to the second one you've created. But a big issue with this is that you can't do arbitrary memory info leaks. You can't read, say, the kernel text to find the gadgets for your up chain. So you can use another object. In this case, I used OS data, which is an object which is used by IOKit, implemented by libkern. And you can use IO service open extended to create them at will from userland. Stefan Hesser had a very nice talk about this, iOS kernel heap Armageddon. It's a bit dated because his techniques don't work anymore, but it explains how libkern objects work, and that's very useful. So you just have to allocate two adjacent VMAP copy structures, corrupt the first one's size, read out the data, change the second structure size to 24, which is the difference between the size of VMAP copy and an OS data object in memory. Write it back, read the second VMAP copy out, causing a wrong free into the calloc 48 zone, which is the zone where OS data lives. And now you have an OS data overlapping a VMAP copies data. And you can redirect to it in userland. And the vtable pointer leaks the KSLR slide. And the data pointer leaks a pointer to arbitrary user-controlled data. So if you change the data pointer and set the capacity to a very high value, so when you free the OS data, it doesn't actually corrupt the data you've just read, you can just use IOKit functions to read out the OS data fairly easily. Here's the memory layout of two adjacent VMAP copies. And then we have some heap corruption. When we free the corrupted structure, this will happen. As you can see, these two objects are essentially overlapping in memory. And so when you create a new VMAP copy, you can't read much, but okay. When you create another VMAP copy, the data of the VMAP copy overlaps the data of the second one, the header of the second one. So you can just control the size and shrink it. And when you free the second one, it will be in a smaller zone, in the OS data zone. So when you create another OS data, this is what happens, and you have read-write access to pretty much everything. And you can also derive the KSLR slide because OS data is a C++ object, and so you can find out a vtable pointer very easily. Okay, this is something new because for this we have to use adjacent allocations. But creating adjacent allocations is not easy. Most heap attacks require them, but the best way right now is to try randomly. But trying randomly, you introduce essentially a probabilistic part of the exploit, because you can try to guess by picking a very high number of allocations to run out the free list and map in a new page, which is then deterministic. But if you don't get it right, you can run out of the page when you do your heap overflow, and that will crash the kernel. So you have probabilistic exploits, but as I said, the layout of newly mapped in pages is deterministic. But mapping pages is expensive. But is it expensive enough to detect it in userland? And the answer is yes. If you can see here, this is in calloc 1024, which has 4 allocations per page. And you can see that every 4 allocations I create, the time it takes to create the allocation essentially skyrockets. And I use a heap info leak over there, so you can see that every time the time spikes, a new page has been mapped in, and all subsequent allocations are adjacent in memory. So yes, it is expensive enough to detect it in userland. A good target to time is vmmap copy in, which is the function which creates our vmmap copy structure. So the general idea is to create a bunch of vmmap copy structures via MAC messages, and then read them out. So we allocate a lot of chunks, put them in the free list, and then when you recreate those allocations, they will be straight from the free list, so you don't have to allocate any new page. So if you keep an average, that will represent an average of the time it takes for the free list to return an allocation, not for a new page to be mapped in memory. And so you just keep those allocated in and keep timing MAC messages. And once in a while, you will have a MAC message which will take much more than normal to create the vmmap copy structure. And when this happens, it's very likely that a new page has been just mapped in. And we already know the number of allocations which should have been added to the free list. As such, we can just keep timing MAC messages, expecting a number which is close to the average. When a time spike is expected to happen, if it happens, we have a full page of adjacent allocations. If it doesn't, we have just failed and we can just retry. You can do this for multiple pages, because if you run out of a page, you create a new page, and if you create the same number of allocations, the page will run out, so you will allocate a new page. You can do this over and over to have additional reliability on your exploit. You can easily craft the heap layout by poking holes in the allocated page. You can just reallocate any object you wish. There is just one catch: you have to limit the number of allocations you create, because if you create too many, the kernel will crash. But on failure, you can just fall back to a probabilistic approach, so this won't hurt reliability of your exploit. This can only increase it. And in some rare cases, precise heap layout control is required to have any form of reliability. An example is IOHID families CVE. This CVE is an use after free I found, which has been fixed in the latest version of Capitain. It's been found independently by multiple parties, and it's been used by Pangu9 as well as my own Nopone exploit. On MacOS 10, it required root to achieve the exploit, but on iOS, you only actually needed a sandbox escape. Essentially, the bug was a textbook use after free. You would create a device and then you would terminate it, but when you terminated this device, you can just keep carrying on operations on it. This will cause use after free. And the core issue is because Apple used the wrong function in the terminate device function. Essentially, what they did was to use OS safe release, which is not safe, to release the object. Instead, what they wanted to do was to use OS safe release null, which is safe and which doesn't cause any use after free. This was not an issue before Yosemite, but for some reason they decided to change the release code into OS safe release, which doesn't do anything particular. So I'm not sure why they did it, but they've done it. So yeah. So here's the virtual call we can do on our use after freed object. As you can see, you can control timestamp, which is the first argument, and you can see this here, controlled register. And the second argument, the first argument of since this is C++, it's a pointer to the object which is freed, and we have full control on this object. So we control the data, we can reallocate another object and just cause a virtual call to corrupt the object itself. We can do this on nosemap OS 10 very easily by just pointing the table pointer in userland and jumping to userland memory. But newer Macs have some new mitigations, SMAP and SMAP. Not many Macs have SMAP, many have SMAP. On nosemap Macs, you can just point the table in userland and do wrap with a KSLR infolic. On iOS, which has both SMAP and SMAP, but the ARM implementation of it, you need to use both a heap infolic as well as a KSLR infolic. But there is an alternate technique to pull this off without having any heap infolic. And this requires a tightly controlled heap layout. Essentially, the trick is that the object which is freed resides in the calloc 256 zone, and the vtable call index is at a very high number. So if you abuse the free list, you can do this essentially. You poke a hole in the first allocation on a chunk of adjacent allocations you control, and then you free the use after freed object. And when you do this, memory layout of the free chunk will look very similar to the C++ object's memory layout, because essentially a free chunk, first 8 bytes are pointer to the next free chunk. And the first 8 bytes of a C++ object are pointer to the vtable. And as such, they're both pointers. And when you do the use after free, the first 8 bytes of the free chunk will be used as a vtable. But it points to our controlled memory. So we can just control the particular chunk of memory which will be the target of our virtual call. And as you can see, the virtual call thinks it's accessing a C++ object, which has a vtable pointer that points to kernel data. But in reality, this is what happens. We can now control the instruction pointer and the second argument. The first argument is a pointer to the use after freed allocation, but the KSLR slide is not leaked yet. In Napone, I used the CAS info, which could be considered cheating, but it's allowed on zip-protected Capitain. And there are also alternative KSLR leaking strategies. You can just abuse the use after free like a type confusion. To further disable system integrity protection, we can just use a function called CSR set all. Pedro Villaja, a CX reverser, discussed this for his rootful kernel extension. And we can just redirect the virtual call to this function. And as long as the first argument is not null, it will disable zip for good. And wrap is not needed for this at all. So I'm a bit early here, so we'll show you the demo. It's actually a video because this particular Mac has been patched. So here you go. This is the kernel version, and I tried to create a file in a system integrity protection protected directory, and it fails, as you can see. But if I run a binary, it will succeed very, very easily. I'm actually a bit early on this, so I will explain better how the kernel exploit itself worked. Sorry. Okay. Essentially, the kernel exploit just use the user after free in the technique I showed earlier to disable SIP by using the jump. Well, I've already explained this. Okay. Okay. So the rapid growth in use of sandboxing technology is pushing many attackers to kernel attacks. Apple has been trying to harden the kernel heap for a very long time, and the Zalog timing attack can be very useful for attackers to essentially determine the heap layout very easily. So I will talk about mitigations for this a bit because I've finished this very early. I'm very I don't know. I'm very. I've rushed this, so I will talk a bit about it. Okay, so for mitigations, XNU kernel does not have many of them. Apple has been trying to improve them, but it hasn't been working much. Attackers keep trying to find new data structures to corrupt to bypass all of their mitigations. So recently, Apple has been changing VMAP copy, but it's not enough, as I showed. A better technique for them would have been to just introduce randomness by using XOR in size of all objects that point to data. Use XOR in most pointers. I would advise to use XOR for C++ vtable pointers as well as free list using different random numbers. And yeah. XOR with the random numbers for pretty much anything related to the heap, which they have been trying to do. I believe that in the newest beta version of Capitain, they've been changing the heap layout of the free list. I haven't done much research on this, but it's breaking my exploits, so I believe that this is what's happening. But it's still not enough because they keep leaving in objects which can be used for the same technique. Yeah, it's not enough what Apple is doing right now. So, yeah. If you have any question about the exploit, I will answer you. Well, I'm so sorry about this, but that I finished so early. But I've been rushing, and I'm pretty. It's my first time speaking, so I'm not really, confident about this. And yeah, I'm very sorry about it. If you want me to explain anything to you, just ask, and I will do my best. I don't know what to do actually right now. Where? Oh, okay. Okay. Yeah. Yeah, essentially, macro binaries have segments. Each segment describes a part of the other space. And most Mako binaries have this page 0 segment, which essentially maps a page which you can't unmap and you can't do anything on. So if the kernel tries to access this page, it will fail because it won't be readable, it won't be writable, it won't be executable, so you can't do anything with it. But essentially what Apple did was to add a check in the kernel to make sure that this page does indeed exist, but there are some very, very old files which do not have the page 0 segment. I've asked Apple about it. They told me that it's software that is on a very important do not break list, so they cannot enforce page 0 on 32-bit binaries because of compatibility reasons. So essentially, if you have a Mako binary which lacks page 0, the kernel doesn't do anything about it, and you can just map anything you want as null. And so you can just call VM allocate to allocate a page at 0, and you can write, read, and execute anything you want of it. Okay, can you deallocate the page 0 of a binary with a page 0? You used to be able to, but since Yosemite, Apple has found out that there are many kernel bugs involving null. I mean, it's not 10 years ago, we had this on Linux. Today, we have this on Mac OS X. People are discovering 0-day, which involves the null page. And so essentially what they did was to prevent all access to the page 0 if a page 0 has been mapped in. But on 64-bit binaries, they just kill your process if you don't have a page 0. On 32-bit ones, they don't. So you can't just unmap it. You have to lock it to do anything with the null page, essentially. Yeah? Okay, I repeat the question. So essentially what you ask is if there are any technical reasons for this. And my answer is no. There are not any technical reasons for this. Apple does not use the page 0 at all. But there is a list of do not break software, and they really care about it for some reason. I don't know why, but I mean, just blocking it would kill an entire class of kernel vulnerabilities, and there are lots of them in the kernel. So, what? Well, you could have a whitelist, but what exactly do you whitelist? Yeah, but I mean, do you do a hash of the binary? Yeah, it's tricky, but Apple, generally speaking, is not good at fixing tricky problems, I believe. They've done an awful lot of mistakes over the years. For example, Gatekeeper is a bit of a joke, in my opinion, because if you have any signed binary which links to an unsigned library, you can just run it and it won't complain. You can just change the library and you have full code execution out of Gatekeeper. The reason why they didn't fix this is the same one why they didn't fix page 0, because there is a compatibility list and they don't want to break it. And I believe that this is a very, very bad technical security point of view for Apple to have. I mean, in iOS, they've been able to achieve great security because they could break the rules, but they don't want to on OS X. And it's a very big problem because many bugs stem from this reason. Any more questions about anything exploitation Apple? Okay. Where can you find the code for it? Essentially, they scan the macro for when you run an executable, they scan for all the segments of memory you describe in your executable. And if there is no segment that describes the page 0, and there is no segment for the page 0, which is essentially not readable, writable, or executable, they kill you. So this is not, as I said, enforced on 32-bit, but on 64-bit, any modification of the segment which involves page 0 will get you killed. Yeah?
There's something that prevents somebody to make an app that enforces the page 0?
There is something that has been introduced in Capitain that prevents this from happening, and it's system integrity protection. With it, you can't actually load any kernel extension without a signature. Essentially, I've made a kernel extension myself. It's on my GitHub called NullGuard, which essentially disables all access to the page, to all binaries which lack a page 0. Stefan SR has introduced in his setYD guard Caxt the same kind of protection. So you can just install his setSwide guard or my NullGuard. But in newer versions, you have to disable system integrity protection for it. So it's not really a good way, in my opinion, to fix it. But yeah, in Yosemite you could. I'm not sure why Apple doesn't do something like if system integrity protection is enabled, block page 0. I have no idea why they don't do it, but it's how they're doing it. So they could very, very easily. It's just like one line of code change. But I'm not Apple, so I don't know their thinking about it. I'm sorry, but okay. If you have any more questions about iOS or OS 6 kernel exploitation. That was it.